Chapter 5, Early Atomic Theory and Structure. And here we start with a lightning bolt. And lightning occurs when electrons move to neutralize charges between different storm clouds and Earth. Ancient religions like the Greek mythologies typically made up some sort of god to explain lightning because there was a huge thunder, there was a lightning bolt which could destroy things, and no one understood what was happening. And so in the ancient world they would make things up to try to explain things. These days we understand the science behind them, and so we know that lightning is just an imbalance of charge. So the Greeks did a lot of work back in those days. Early models of all the atoms were developed by the Greeks. And Empedocles proposed that matter was composed of the four basic elements: earth, air, water, and fire. Democritus proposed that matter was composed of small indivisible particles he called atoms, coming from the Greek word atomos. Atoms could combine in different ways, giving a rise to the diversity of the compounds that we observe. However, Aristotle, who was an extremely influential philosopher during his time, supported Empedocles' theory, so the atomic theory was not fully accepted until 2,000 years later. And so the theory of earth, air, water, and fire existed a lot longer than you would have expected based on the merits of the theory itself, just because the people peddling it were so influential. Now there's a huge gap here. We go from the ancient Greeks 2,000 years ago to Dalton in 1800s. And so in between were the Dark Ages, which societies fell backwards and nothing new was really done. And it wasn't until about the Renaissance period in the 1600s that the world re-embraced science, and science really started advancing rapidly again. So here's Dalton's theory of atoms proposed in the early 1800s, and it stated that elements are composed of small indivisible particles that he called atoms, and that atoms of the same element are identical in mass and size, and that atoms of different elements differ in their mass and size. And we're going to talk about these three later because with subsequent research in science, we've realized that these three are not totally correct, and we're going to talk about those exceptions in a second. But 4, compounds are formed by combining 2 or more atoms of different elements. We still believe that to be completely true. Atoms combine to form compounds in simple whole number ratios. We still believe that. And atoms of 2 elements can combine in different ratios, forming totally different substances, and that will be the law of multiple proportions. And so water and hydrogen peroxide, H2O and H2O2. Both compounds are completely made out of hydrogen and oxygen, but they're combining in different ratios, and thus they are forming completely different substances. So most of Dalton's theory remains valid today. However, we now know that number 1, he said that atoms are composed of small indivisible particles called atoms. We know that atoms are not indivisible. They can be broken down. He made this postulation before radioactivity was discovered. And so now the atom has been broken down into its subatomic particles, so the proton, neutron, and the electron. And then protons and neutrons can be broken down into quarks. And so there's actually a lot more particles than he was aware of in the 1800s. And so elements can decompose, and radioactive elements do decompose. Not all atoms of the same element have identical mass. So we look at the isotopes: carbon-12, carbon-13, and carbon-14. They're all carbon, but they have different masses. Not the same, because carbon-12 has 6 neutrons, carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. And so they have different masses. Atoms are not indivisible. Atoms are composed of subatomic particles. If we go back to number 3, atoms of different elements differ in their mass and size. That's also not true. Because of isotopes, you can have a carbon-14 and a nitrogen-14, and they are both the same size and mass, even though they're different elements. So carbon-14 is 14 atomic mass units, and so is nitrogen-14. And so the first 3 of Dalton's model don't fully apply anymore. There's been a couple exceptions, but still overall it was a great theory, and it was the first major theory in chemistry in a really long time, so it was really substantial. Properties of electric charge. Charge can be either positive or negative. Opposite charges attract. Like charges repel. So negative and positive attract each other. Whereas two negatives will always repel each other, and two positives will always repel each other. Charge can be transferred from one object to another by contact or induction. And here we have a formula that relates to the force of attraction or repulsion. It is a constant K, that's the constant, times the charge on species 1, Q1, can be positive or negative, times the charge on species 2, divided by radius squared. As radius is in the denominator, as the radius gets bigger, as two objects get further and further apart, this denominator gets bigger and bigger and bigger, and so something divided by a gigantic number is basically 0. So think of 1 divided by 10 trillion. It's almost 0. And so as things get further apart, the force of attraction or repulsion gets littler. As things get closer together, the force of attraction or repulsion gets bigger and bigger and bigger. Because as radius gets less and less and less, now you have a smaller number in the denominator, and that gives you a huge force. So like 1 divided by 0.1 is 10. 1 divided by 0.01 is 100. 1 divided by 0.001 is 1,000. And so as the two objects get closer and closer and closer together, we'll see the force of attraction or repulsion skyrocket up. Michael Faraday, he was an English scientist who discovered electrolytes. And electrolytes, you'll probably see this in Gatorade or Powerade, they are just compounds that when they dissolve in water, they form charged ions, and those charged ions can conduct electricity. And so when a sports drink says it has electrolytes, what they really mean is there's salt in there. Usually it's got about 3% sodium chloride and like 1% potassium chloride. And those are typically the electrolytes that are used in the sports drinks. Faraday also discovered that some compounds decompose in water into their elements. And he saw that these elements could be attracted to either a negative cathode or a positive anode. He named these charge elements ions because they had a charge. Because they were being attracted to an electrode under an electric field, they were no longer neutral. They were electrically charged. And so he named them ions. And here we see a light bulb, and it glows when we put salt in here because salt water conducts electricity, so electricity can move easily from electrode to electrode. Pure water does not conduct electricity. However, once there's ions dissolved in it, water does conduct electricity. So tap water or well water easily conduct electricity, but absolutely pure scientific grade water will not conduct electricity because it's not the water that's actually conducting the electricity, it's the electrolytes which are dissolved in the water. Arrhenius extended Faraday's work. He proposed that ions are atoms that carry positive or negative charge. And the positive ions got named cations because they were attracted to the negative electrode, the cathode. So the cations were the ions that migrated to the cathode. The anions were the negative ions which were attracted to the positively charged electrode, the anode. So the anions were the ions that migrated to the anode. Cations moved to the cathode, anions moved to the anode because opposites attract. The positively charged ions wanted to move to the negative electrode. The negative ions wanted to move to the positive electrode because opposite charges attract. Based on Faraday's and Arrhenius' work, Stoney proposed the electron was a fundamental unit of electricity associated with atoms. And J.J. Thomson later experimentally confirmed the existence of electrons. So single atoms are tiny. They're super tiny. The diameter is about 0.1 nanometers. So because atoms are so small, determining the presence of subatomic particles was really difficult. However, new instruments in the early 1900s permitted detection of these particles. And here we see copper. And this is a scanning tunneling microscope. And basically, this is just a machine that drags the world's most sensitive needle over an object. And it's so sensitive that the electrons at the tip of the needle are repelled by the electrons of the atoms it's gliding over. And so it's just a needle that is so sensitive it actually has electron resolution, which is why we can see these individual copper atoms, giving definitive evidence of the atomic theory of matter, that that materials and matter comes in discrete units called atoms.